Hi, in this video we're going to talk about some commonly tested continuous distributions. So we're switching gears from discrete distributions, commonly tested discrete distributions, to commonly tested continuous distributions. And I'm going to just give you sort of the same order of things that we did with the discrete case. I'll give you the name for the distributions and then rules for density and distribution functions, expected value, variance, and so forth. For the uniform distribution, I'll give you all of this information also for the exponential distribution. The exponential distribution is going to generalize to a what's called a gamma distribution, and we're not going to talk about the distribution function on the gamma distribution, but we're going to start with the uniform distribution, then the exponential distribution that extends to the gamma. By the time we get to the gamma distribution, I'm not going to talk about so much the distribution function. It's not really an easy way to calculate distribution function, so I'm not really going to talk about that. We will talk about expected value and variances of the gamma distribution. And likewise with the beta distribution, kind of the same setup with the gamma distribution. This other one called the beta distribution. Distribution function is not an easy, rule or formula for calculating values of the distribution function for gamma or beta distributions. And then normal and log normal distributions, it's not really an easy, simple rule for calculating especially the distribution function, and the density function is kind of complicated too. I probably won't, or I don't plan on giving you the rule for the density function either. You just need to know how to work with normal distributions, and I'm sure you've seen this in your classes before. Log normal distribution is going to be kind of a transformation of a normal distribution, so we're going to kind of relate, when we see a log normal distribution, we'll just kind of relate it back to a corresponding normal distribution. But we'll get to all of that in the next few videos. But in this video, I do want to go ahead and get started with the uniform distribution. So we're in the case of a continuous uniform distribution. I want to give you these properties with respect to this continuous uniform distribution. I'm going to denote it like we had been denoting distributions all along. So I'll use this cap x tilde cap u for a uniform distribution. And then I'll put a parentheses a comma b. And that parentheses a comma b, I'm using interval notation. So this is defining the support of the random variable. This random variable continuous uniform distribution is defined over an interval of values, the interval from A to B. In comparing that to the discrete uniform distribution, this is how we denoted the discrete uniform distribution, and notice that it was just defined on a discrete set of values. So the continuous uniform distribution defined on an interval of values, of course that's a continuous interval there, and then discrete uniform distribution is defined on a discrete set of values. Okay, so if you remember, the discrete uniform distribution was defined, or we could recognize it as being a distribution where all of the probabilities in our probability table were constant, were equal to each other and constant. And that's going to define the continuous uniform distribution too. When we see a density function that is, this density function is constant. It's constant with respect to the variable x. There is constant with respect to x. So when you see a constant density function, then you're dealing with a uniform distribution. Let's move on and look at the distribution function. The distribution function is defined to be this probability, and once we have that the density function, we have a rule defining the density function, then the distribution function is just an integral of that density function over the values defined by cap x being less than or equal to z. Notice I'm using z in this case as the placeholder variable for the distribution function, because I'm using x as my variable that I'm integrating with respect to. So it wouldn't be good notation to use a x as also a limit of integration. So I'm using z as the placeholder variable for the density function here. And to say that cap x is less than or equal to z in this case, because cap x is defined over the interval from a to b, cap x can't be any value less than a. And so to say that cap x is less than z is really to say that cap x is between the parameter a and z. And so I'm integrating from a to z. I'm integrating this density function. I'm going to plug in this constant 1 over b minus a for the density function. And then when you integrate a constant over an interval, you just get that constant 1 over b minus a times the length of the interval over which you're integrating, which is a z minus a. And so I get that my punchline here is that the density function, the distribution function evaluated at z would it be equal to a z minus a divided by a b minus a. Now, z was just a placeholder variable, so when I go to the next slide here, I'm just going to replace the z by an x, because what you see in red, I don't have, in the expression on the right in red, I don't have any x's there, so it's okay for me to use an x now. So I'm just going to go back to using x as the placeholder variable for the function. So the density function, the distribution function is now defined as an x minus a divided by b minus a. And notice that that's a linear function with respect to x. So anytime you see a linear distribution function, you're dealing with a uniform, a continuous uniform distribution. I want to talk about probabilities a little bit more in detail, a little bit more. So let's just look at a general probability. Say that the random variable cap x is between some value c and another value d. So it's really easy to calculate probabilities with these uniform distributions. So I want to show you that. And so first thing I'm going to recognize is that the random variable cap x is defined over the interval from a to b. And so if I look at that interval from a to b, the length of that interval is b minus a. And so I'm going to get an expression for that probability that's going to be a fraction, and the denominator is going to be that b minus a, the length of the interval that's defining the support of that continuous uniform distribution. The next thing I do is I look at the event that I'm taking the probability of, and that's, in this case, it's the event that the random variable is between a c and a d. Now I'm assuming that c and d are both between A and B, and C is less than D, so you got these sorts of things. And so I'm looking at, it doesn't make sense if you don't assume that C is less than D, and they're both between A and B. So if you look at the interval now from C to D, I look at the event, and the event is defining an interval from C to D, and the length of that interval from C to D is D minus C. So that's what's going to go in the numerator of this expression. So once again, the probabilities, when you calculate probabilities, when you have a continuous uniform distribution and you're calculating a probability of some event, in the denominator, it's going to be, the result is going to be a fraction, and in the denominator, you're going to put the length of the interval that is defined by the random variable itself, in this case, b minus a, and in the numerator, you're going to look at the event, and the numerator is going to be the length of the interval that defines the event. Okay, I want to kind of relate this back to what we did with the distribution function just a second ago, because remember, the distribution function I have highlighted in red is just a probability itself. It's the probability that the random variable cap x is less than or equal to whatever the placeholder variable is, in this case an x. So again, what I do is if I want to calculate this probability, I don't really remember the formula there, the top formula for the one that's linear with respect to x. I just do the problem. I look at, first of all, I look at the random variable. It's defined over the interval from a to b, so I know that the length of that interval is b minus a. So my probability is going to be an expression with a b minus a in the denominator, and in the numerator, I'm looking at the event that cap x is less than the value x is defining an interval from a to x. And so the length of that interval is x minus a. And so my result is I'm getting the same result that I had before, that the distribution function evaluated at x is a ratio in the numerator an x minus a, and in the denominator a b minus a. Okay, so let's move on. Let's look at expected values now. So this is the definition of the expected value. It's the integral of an x times the density function over the support of the random variable. So this is from a to b. The density function is constant now, so it's a 1 over b minus a. I can factor that out because it's a constant, and then I'm just integrating an x dx that integrates to the simplest antiderivative of x is x squared over 2, evaluated from a to b. Plug in a b and subtract off what you get when you plug in an a, and I get this expression. And the next thing I'm going to notice here is that the numerator, b squared minus a squared, will factor as a b minus a times a b plus a, and then I can factor off the b minus a in the numerator with the b minus a in the denominator. And I'm going to rewrite the second. I'm going to rewrite what's in the numerator there, the b plus a. I'm just going to rewrite it as an a plus b. And so my punchline is then that the expected value of a continuous uniform distribution over the interval from a to b is just a plus b over 2. And notice that that's just the average of the parameters of a and b. So just average the values a and b, and you'll get what the expected value of the random variable is. I'm going to just kind of give you the punchline on the variance of cap x. It's this expression of b minus a squared over 12. I'll leave it to you to show that, and you can show that by using the fact that it's the second raw moment minus the square of the first raw moment, and you can go through the process if you like to verify that formula, but that's just the punchline, is that you're going to get a b minus a, the square of b minus a, and then divided by 12. So again, remember that b minus a is just the length of that interval that's defining the distribution. So you're squaring the length of the interval that's defining the distribution, and then you're dividing by 12. Okay, let's look at an example. This is a SOA sample question that has, it's an example with respect to uniform distributions, and as you'll see, it has both continuous and discrete examples in here. So we got automobile claim amounts are modeled by a uniform distribution on the interval from 0 to 10,000. Actuary A reports cap X, the claim amount divided by 1,000, and Actuary B reports cap Y, which is cap X rounded to the nearest integer from 0 to 10. And now we want to calculate the absolute value of the difference between the fourth moment of cap X and the fourth moment of cap Y. So let's start. I'll slow down in just a second, but let's just start with solution with defining a random variable cap C to be the random variable that's representing the automobile claim amounts, and we're told that we're modeling this with a uniform distribution over the interval from 0 to 10,000. We're told it's on the interval 0 to 10,000, so we're dealing with a continuous uniform distribution. And then we're told that cap X, Actuary A is reporting cap X, which is just the claim amount, so that will be cap C divided by 1,000 here. Now what Actuary Y is doing, so if you think about the values cap X, if you're taking any number between 0 and 10,000 and you divide it by 1,000, you're going to get a number between 0 and 10. And that's on the interval from 0 to 10, because the cap C value started on an interval from 0 to 10,000, and it could be anything from 0 to 10,000. Divide that by 1,000 and you're going to get anything between 0 and 10. So cap X is a continuous random variable. And then cap Y, it says, is the cap X value rounded to the nearest integer from 0 to 10. And we'll come back to this in just a second, but what cap Y would be then is a discrete, it would be a discrete random variable on the values 0 or 1 or 2 or 3 or 4 all the way up to 10. Those are the values for cap Y. Again, we'll come back to that in just a second. All right, so now the question is to calculate the absolute value of the difference between the fourth moment of cap X and the fourth moment of cap Y. Well, first of all, the fourth moment of cap X is cap X to the fourth power, which would be the same as cap C to the fourth power divided by 1,000 to the fourth power. And I want the expected value of that, so I use properties of expected value to say, well, then I just need to calculate the fourth moment of cap C and divide that by 1,000 to the fourth power. That would give me the fourth moment of cap X. Okay, so let's start with the numerator in that last fraction, the fourth moment of cap C. So that would be an integral of C to the fourth times the density function for C over the support of cap C, which is from 0 to 10,000. And then what's the density function for cap C? Well, it's 1 over b minus a. It's 1 over the length of the interval. So the length of the interval is 10,000. So the density function for cap C is a 1 over 10,000. And when you evaluate the integral of c to the fourth times that 1 over 10,000 over the interval from 0 to 10,000, I'm getting a 1 over the 10,000 that I factored out. I'm getting a c to the fifth over 5 that I'm then evaluating from 10,000 to 0. So the result is just the result here is when you do the product, go through the calculation, we'll get a 10,000 to the fourth divided by 5. Now that's what the numerator is. So I got to go back then and to get my fourth moment of cap x, I divide that by 1,000 to the fourth, and when I do the arithmetic there, I get just 2,000. So 2,000 is going to be my answer then for the fourth moment of cap x. So now let's look at the cap y random variable. Like we mentioned a little while ago, the cap y random variable will have values 0 or 1 or 2 or 3 all the way up to a 10. So let's look at the p sub 0 value. This is a discrete random variable. The cap y is discrete. Let's look at the p sub 0 value. That's the probability that cap y is 0. How did you get a cap y of 0? Well, cap y is the cap x random variable rounded to the nearest integer. So to say that cap y is 0 is the same as to say that cap x is between a 0 and a 0.5. And now, how did you get a cap x value between a 0 and a 0.5? Well, that came from having a cap c value between a 0 and 500. So I'm relating it all the way back to the cap c, which I know the distribution for cap c is this uniform distribution. And so the calculation for this probability will be a fraction. In the denominator, I'm going to have the length of the interval that defines cap c, which is 10,000. And in the numerator, I look at the event, and the event is that cap c is between 0 and 500, and the length of that interval is 500. So I end up with 500 divided by 10,000, which is a 0.05. So p sub 0 value is a 0.05. Likewise, p sub 1 is the probability that cap y is 1. The way cap y was 1 is that it was rounding off cap x to the nearest integer. So that would say that cap x was between a 0.5 and a 1.5. I don't really need to take into account I've written the inequality there, this last inequality that has the cap x. I think I've done this the correct way, that cap x would be greater than or equal to 0.5 but less than 1.5. But the way that would happen is if cap c was greater than or equal to 500 but less than 1,500. But again, now cap x and cap c are continuous random variables, so it doesn't really matter if I get the endpoints, if I'm including the endpoints or not. But I've been careful here with including the left endpoint but not the right endpoint. But again, you'll get the same value because of the continuity of the random variable, whether or not you use the endpoints or not. So cap y equals 1, though, would mean that the claim amount was between a 500 and a 1,500, and the probability that the claim amount was between 500 and 1,500 would be a ratio in the denominator would be 10,000, because that's the length of the interval that's defining the support, and in the numerator we would get the length of the interval that's defining the event is 1,000. And then 1,000 divided by 10,000 is 0.1. So the P1 value would be 0.1. I think you should probably be able to see and agree with me. The P sub 2 value, I would go through a very similar argument, and I'm going to see that the P sub 2 value is going to be 0.1. And all of the other P values, P sub K values, all the way up to 0.9, all the way up to 9. The P sub 9 value would be 0.1. The P sub 10 value would be a little bit different. It's a little bit different, kind of like the P sub 0 value is a little bit different. The P sub 10 value would be the probability that cap y is 10. That would say that cap x was between 9.5 and 10. So cap c would have to be between 9,500 and 10,000. And that probability is going to be 0.05, kind of like the probability with the P sub 0 value. So I got all these probabilities. The P sub 1 through the P sub 9 value are the same, but then the P sub 0 and the P sub 10 value are, they're the same as each other, but different than the other values. So I don't really have a uniform distribution here because they're not all exactly the same, but it's kind of close to it. The question, though, is now what's the fourth moment of cap y? So I don't really need to know at this point, the fourth moment of cap y is the sum product of the y to the fourth power with the probability. So watch what I do in the next slide. I'm going to replace the y column there in the next slide with a y to the fourth column, and then I take the sum product. And when I do that, I did not include the first product in the sum product because 0 to the fourth is 0. So I get 0 times a 0.5 I didn't put in there. But then I get a 1 to the fourth times a 0.1, 2 to the fourth times 0.1, and so forth. I can factor out a 0.1 from all of that. and just kind of go through the arithmetic there. The last factor, I should say, is a 10 to the fourth times the 0.05. But if you go through the arithmetic there, I got a 2033.3 when I did the arithmetic there. And so the absolute value of the difference between the fourth moment of cap x and the fourth moment of cap y would be the absolute value of the 2000 and the 2033.3, and that absolute value of that difference is 33.3. Okay, so that does it for, that's our example. That would be our answer. Nice little problem that the SOA has come up with there. This was our first commonly tested continuous distribution that we were talking about. The next one is the geometric distribution that generalizes to the gamma distribution, and we'll talk about that in the next video. All right, I'll see you there.